across an entire galaxy is not dealing with a few isolated journeys. It is dealing with tens of billions of gravitational wells, each one requiring energy to enter and exit. Stars are not evenly spaced platforms waiting to be used. They are deep potential wells embedded in a larger gravitational structure. Every transition between them has a cost, and those costs accumulate in ways that are easy to underestimate when drawn on a flat diagram. Even if a civilization had access to the energy output of an entire star, like in the Kardashev Type II framework, that does not automatically solve the problem. Having energy is not the same as being able to freely convert it into large-scale motion across gravitational gradients. The universe is not just an energy economy. It is an energy plus gravity economy, and gravity continuously imposes inefficiencies on every attempt to expand outward. And this is where the picture starts to shift, because if expansion is this expensive, then the absence of visible expansion across the galaxy becomes less mysterious. It is not necessarily evidence that nothing is out there. It may simply be evidence that large-scale expansion is not a natural outcome of intelligence once physical constraints are fully accounted for. At that point, the question stops being about why we do not see other civilizations and starts becoming a more grounded physics question about what kinds of civilizations are actually compatible with a universe structured like this. A universe where movement is costly, where escape is expensive, and where every step outward demands more energy than intuition initially suggests. And once you follow that logic far enough, you begin to realize that the real limitation may not be intelligence at all. It may be the geometry of space-time itself, quietly shaping what intelligence can realistically become on cosmic scales. Once you follow that logic far enough, the picture becomes even more restrictive because you start to see that gravity is not just slowing down travel, it is shaping the entire architecture of what a civilization can realistically build and maintain. Even communication, which is often treated as the easy alternative to physical expansion, is not free of these constraints. We tend to imagine sending signals across the galaxy as simple. Point a transmitter, send a message, wait for a response. But in reality, every signal is still bound by the same physical rules that govern everything else in the universe. Photons travel at the speed of light, but they are still affected by distance, dispersion, and background noise. Over interstellar scales, signals weaken dramatically. They spread out according to the inverse square law, meaning that by the time they reach another star system, they are incredibly diluted. On top of that, they must compete with natural background radiation, including the cosmic microwave background, which fills the entire universe with a persistent noise floor. So even communication is not simply a matter of sending information. It becomes a matter of overcoming noise, distance, and energy loss simultaneously. The further you try to reach, the more energy you must invest, just to make your message detectable. And that makes large-scale communication networks far more expensive than they appear in simplified models. This matters because many arguments about extraterrestrial civilizations assume that communication is cheap and expansion is optional. But if both travel and communication are expensive in the same fundamental way, because both are constrained by gravity and space-time, then the entire framework changes. Now consider what this means for a civilization trying to operate at a galactic scale. It is not just coordinating across distance. It is coordinating across delays measured in years, decades, or even millennia. A message sent from one star system to another is not a conversation. It is a historical record arriving long after the conditions that produced it have already changed. That kind of delay does more than slow communication. It breaks coherence. Any distributed system that spans light years loses the tight feedback loops that make coordination efficient. Decisions become outdated by the time they are received. Plans become misaligned with reality. The larger the system grows, the more fragmented it becomes. So even if a civilization could physically spread across the galaxy, maintaining it as a single unified structure becomes increasingly difficult. It would not behave like a single intelligence. It would behave more like a collection of loosely connected, semi-independent regions, each adapting to its own local conditions. And that leads to a very different expectation than the one often assumed in discussions about advanced civilizations. Instead of a galaxy filled with coordinated expansion and visible engineering on massive scales, you might expect something far quieter. Not absence, but isolation. Not expansion, but containment within local gravitational systems. At this point, gravity begins to look less like a background force and more like a kind of universal boundary condition. It defines how far information can travel coherently, how far matter can move efficiently, and how far any system can expand before losing internal structure. And once you see it this way, the silence of the universe starts to look less like a mystery waiting for an explanation and more like a natural outcome of how physics organizes complexity across space. Once you start viewing gravity as a boundary condition rather than just a force, the next layer of the argument becomes even more unsettling because it connects directly to information itself. We usually think of civilizations as information systems. They store knowledge, process it, transmit it, and build technology on top of it. From that perspective, you might assume that as civilizations become more advanced, their ability to handle information should scale smoothly. More computation, more coordination, more intelligence distributed across space. But physics places a hard limit on that assumption in a way that is not intuitive until you look closely at how space-time behaves. One of the deepest results in modern theoretical physics is the holographic principle. It suggests that the maximum amount of information you can store inside a region of space is not determined by its volume, as you might expect, but by its surface area. That alone is already a radical shift in how we think about reality. It means that as you try to pack more and more information into a region, you eventually run into a limit set by geometry itself. And if you push beyond that limit, the system does not simply overflow. It collapses into a black hole. Gravity intervenes and reorganizes the structure of space-time in a way that prevents unlimited information density. So now you have a second constraint layered on top of energy costs. Not only is it expensive to move through space because of gravitational wells, but it is also fundamentally limited how much information any region of space can hold or process. This has major implications for how we imagine large civilizations. A galaxy-spanning intelligence is often pictured as a unified, coordinated system, like a single mind spread across space. But the holographic limit suggests something very different. The further you spread information physically, the more constrained and fragmented it becomes. And when you combine that with the speed of light limit, the picture becomes even more restrictive. Information cannot propagate instantly. It takes years, decades, or longer to move between distant parts of a galaxy. That delay is not just a communication lag. It is a structural barrier to coherence. What you end up with is not a single integrated intelligence, but a distributed system that is constantly out of sync with itself. Each region of such a civilization would be operating on outdated information about the others. Coordination becomes approximate rather than precise. Unity becomes statistical rather than real. This changes the way we interpret the idea of advanced civilizations. Instead of imagining something that grows outward and becomes more unified and visible, physics suggests something that may grow inward in complexity but outward in fragmentation. More knowledge locally, but less coherence globally. And this brings us back to the original question about silence. If civilizations are constrained in this way by gravity, by energy costs, by information limits, then large-scale expansion may not be the natural endpoint of intelligence. It may actually be the least stable configuration. A civilization might become extremely advanced without ever becoming visible across interstellar distances. It might optimize locally, deepen its control over its own system, and gradually reduce its interaction with the broader galaxy simply because the costs of expansion outweigh the benefits. From the outside, such a universe would look empty. But that emptiness would not necessarily reflect absence. It would reflect limitation. And once you reach that conclusion, the Fermi paradox stops being a question about missing signals and starts becoming a question about what kinds of intelligence are even physically viable in a universe structured this way. The universe is 13.8 billion years old, filled with hundreds of billions of stars in our galaxy alone, and yet after all that time, across all that distance, we still have no confirmed sign that anyone else is out there. No reliable signal, no verified probe, no unmistakable evidence that we are being watched or contacted. At first glance, that silence feels like loneliness. But when you look at it through physics instead of emotion, it starts to feel less like loneliness and more like something we may be misreading entirely. Because true loneliness would mean something very specific, that we have actually searched the universe in a meaningful way and found nothing. But that is not what we have done. In reality, we have pointed radio telescopes at a tiny fraction of the sky for a few decades. In cosmic terms, that is not a serious survey. It is closer to dipping a teaspoon into the Pacific Ocean and concluding there are no fish anywhere in it. The absence of a signal in such a limited search does not tell us much about what is actually out there. It only tells us how little we have been able to look. That kind of loneliness is not a deep mystery. It is an engineering limitation. We can build better instruments. we can observe longer, and we can expand our search. That problem is solvable in principle. But there is another layer to this question that feels much less comfortable. It is not about how little we have looked. It is about what the universe actually allows. Once you start looking at the energy requirements behind interstellar communication, exploration, and expansion, the question changes. It stops being, "Where is everybody?" and becomes something far more fundamental. Does the universe even permit the kind of expansion we assume intelligent life would naturally pursue? I have spent a long time thinking about the Fermi paradox, not as a curiosity, but as someone working with the structure of space-time and gravity at extreme scales. And what often gets missed in popular discussions is that the problem is usually framed in terms of biology or sociology. People talk about civilizations destroying themselves, or failing to develop, or simply choosing not to expand. Those are possible explanations, but they may not be the most important ones. The missing variable is physics, more specifically, gravity, and what it actually costs to move through a universe shaped by it. Every object with mass exists inside a gravitational potential well. This is not a metaphor, it is a geometric fact of space-time. Einstein showed us that mass curves space-time, and that curvature behaves like a kind of well. To move out of it, to climb from a lower gravitational potential to a higher one, requires energy. That cost is not optional. It is not something technology can remove. It is written directly into the field equations of general relativity. On Earth, that reality shows up as escape velocity, about 11.2 kilometers per second. That number is not arbitrary. It comes directly from the strength of Earth's gravitational field. It is the minimum speed needed to leave without falling back. And as soon as you begin to scale that idea beyond Earth, the numbers start to become less intuitive and far more constraining. Because gravity does not just hold planets together. It defines the energy landscape of everything that exists. Now, we begin to see why interstellar expansion is not just a question of technology or time. It is a question of whether enough energy exists, and whether any civilization, no matter how advanced, can realistically afford to spend it at that scale. And once you start following that line of reasoning, the universe begins to look less like an open frontier waiting to be explored, and more like a structured landscape where every movement has a cost that cannot be avoided. If the universe is so vast, 13.8 billion years of history, hundreds of billions of stars in our galaxy alone, then one question becomes almost unavoidable. Why has nothing ever answered back? No signal, no probe, no trace of engineering drifting across a star's light. At first glance, that silence feels like loneliness. But the deeper you think about it, the more it stops feeling emotional and starts feeling suspicious. Because real loneliness would have a very specific meaning in science. It would mean we looked properly across a meaningful portion of the sky for a meaningful amount of time and found nothing at all. But that is not what we have done. We have taken incredibly narrow slices of the cosmos, pointed our instruments at them for a few decades at most, and then drawn conclusions about the entire universe. In cosmic terms, that is like dipping a single spoon into the ocean and deciding it contains no life. The absence of a signal in that tiny sample doesn't actually tell us very much. So if there is a kind of loneliness here, it is not yet proven. And that version of uncertainty is actually manageable. It just means we need better instruments, longer observation times, and smarter strategies. The real discomfort begins when you stop focusing on detection limits and start focusing on energy itself. Because once you do that, the question shifts. It is no longer, where is everybody? It becomes something far more precise and far more uncomfortable. Does the universe even allow the kind of behavior we expect from advanced civilizations? To approach that, you have to leave biology and sociology aside for a moment. Not because they are irrelevant, but because they are not the limiting factor. The real constraint is something much more fundamental. It is gravity. Everything we know sits inside a gravitational structure. Planets, oceans, cities, and civilizations are all located inside what physics describes as potential wells. That is not just a metaphor. In general relativity, mass literally curves space-time, and that curvature creates a kind of geometric depression. To move out of it, you must spend energy. There is no workaround. There is no negotiation with the equations. On Earth, that cost shows up as escape velocity, 11.2 kilometers per second, just to leave the planet without further propulsion. That number is not arbitrary. It comes directly from the energy required to climb out of Earth's gravitational field. And it is already extreme. It is about 40 times faster than a bullet. Now scale that idea up. Imagine not just leaving Earth, but building systems that can leave the solar system or even move between stars. The rocket equation, developed by Konstantin Tsiolkovsky long before modern spaceflight, tells us something crucial. Every increase in speed demands an exponential increase in fuel. Not linear, not gradual. Exponential. This is where intuition breaks, because people tend to imagine space travel as a scaling problem. More technology, more efficiency, more progress. But the physics does not behave that way. The deeper you go into gravitational systems, the more expensive every step becomes. It is not a road you can simply optimize your way out of. And this is the first major correction to how we usually think about civilizations in space. We often assume that if intelligence increases, expansion follows naturally. More energy, more reach, more presence. But that assumption quietly ignores the fact that every star system is not just a destination. It is also a gravitational trap. Leaving one requires paying an enormous energy cost. Entering another requires paying again. So even before we consider communication, engineering, or intention, we are already dealing with a universe that charges a toll at every stage of movement. And that toll is written directly into the geometry of space-time itself. That is where the real analysis begins. Because once you accept that gravity is not a background detail but the dominant cost of large-scale motion, the Fermi question stops being about silence and starts being about feasibility. And what comes next is where that idea becomes even more difficult to ignore. What comes next is where this idea becomes harder to dismiss. Because once you accept that gravity is the dominant cost in moving through the universe, you start to see that it quietly controls almost every ambition we usually assign to advanced civilizations. Take interstellar travel, for example. It is often described as an engineering challenge, as if better materials or smarter propulsion systems would eventually make it routine. But the real constraint is not engineering. It is energy, and more specifically, the amount of energy required to escape and re-enter gravitational wells over and over again. Even reaching the nearest star system is not a simple extension of current spaceflight. Proxima Centauri is about 4.2 light-years away. That distance sounds manageable when spoken casually, but it translates into roughly 40 trillion kilometers of empty space. To cross that gap, in any meaningful human time frame, a spacecraft would need to travel at a significant fraction of light speed. At those velocities, the energy cost becomes staggering. Accelerating even a small payload to a fraction of light speed requires energy on a scale comparable to the total output of large power stations running continuously for long periods. And that is only the acceleration phase. Deceleration at the destination requires a second, equally expensive energy investment. There is no free arrival. Physics demands payment in both directions. This is where the rocket equation becomes more than a formula on paper. It becomes a kind of structural limit on what civilization can physically do. Every additional kilogram of payload increases fuel requirements, which increases total mass, which increases fuel requirements again. The system feeds back on itself in a way that rapidly becomes extreme. What looks like incremental scaling turns into exponential growth in required resources. So when we imagine a civilization expanding across star systems, we are not just imagining technological progress. We are implicitly assuming that such a civilization can sustain enormous energy expenditures repeatedly across millions of years without ever collapsing under the weight of its own logistics. That is a very strong assumption. Now, extend the scale even further. A civilization that attempts